Momentum and collisions now. So still talking about momentum, but looking at what happens when things are colliding. We talked before about how momentum is always conserved, and it's true in collisions as well. I'm going to show you a video to start out with here. And
conservation of momentum tells us that the total momentum in any closed system will remain the same all the time. And since momentum is equal to mass times velocity, even if you have multiple objects going at different speeds that might collide, for example, the total momentum of the system before and after the collision will remain constant. So, for example, these two balls, which in this case happen to be of equal mass, whether one of them is moving and causes the other to move, or they're both moving and collide and move off in different directions, the total speed and the total mass of the entire system always remains the same. So, for example, if this had a velocity of 0, and that had a velocity of 1, the first one might impart some of its momentum onto the second, but the total between the two remains the same. And that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other. It even works, in this case I put Velcro, it even works if these two stick together. The total momentum remains the same.
right, so all sorts of different types of collisions there. That video is this link here, if you want to see it again, or if you couldn't hear it well or whatever. So yeah, we're only looking at linear, so straight line, x direction only momentum as a start, just as a way to start working our way through this. But you can see in the video, obviously, end up with 2-dimensional and even 3-dimensional analysis of conservation of momentum. And I'll mention more about that in a second here. But yeah, the total momentum in each direction is the same. And so we're going to be looking at the x direction. Where's my file here? Down here, I think, is where I do it. I'll come back to this. But basically, you can think of the conservation momentum just in general or in particular directions. So I'll come back to that. Okay, but as we said before, total momentum, loss of concentration momentum is always conserved. So now we're saying it in terms of the total momentum of an isolated system is always constant. So you can make an object increases momentum, but it's by you pushing on it, right, separately. And so if you look at you and the Earth and it and so on, the momentum of the whole system is conserved. So initial momentum will always equal final momentum, and that the symbolism for that is often this: P equals P prime, or initial momentum equals final momentum. So let's make note of that. That little apostrophe is called prime. It means the final value. Okay. All right. So linear collisions between mass 1 and mass 2. Looking at this situation here, we got mass 2 coming in from the right, traveling left. Mass 1 coming in from the other side, traveling to the right. So we might designate, say, to the right as our positive x direction. In which case, the momentum in the initial, so this is initial momentum, just by P, right? So you can tell that's initial. And then this one down here is final. So yeah, mass 1 times its velocity, mass 2 times its velocity, right? And notice because of vectors here, this one would go in as a positive number, and this one would go in as a negative number. Just because of the directions, right? And then the final velocities here and so on, we'd have the final momentum being m1 times v1 prime and m2 times v2 prime. So mass 1 times its final velocity, in other words, right? Notice this is now going to be a negative number of some sort. And this is going to be a positive number of some sort. The way it's going to work out, based on seeing something collide, picturing that being able to happen and so on, right? And so we're told, we know, like we've been told that the momentum's always conserved. And so we know that the initial momentum and final momentum are the same. So we have this equation that means that, right? The m1v1 plus m2v2, in other words, the total momentum at the start. And you could have as many objects as you want, m3, v3, m4, v4, and so on. So initial momentum equals final momentum. Okay, so it's kind of a tongue twister, but m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. And again, that's a guaranteed thing. Okay, that's always true. So let's look at a simulation of this. So I'm going to just reset this thing. And so we've got the momentums, right? So we have the momentum of the little one is 0.5, and the momentum of the big one is negative 0.75, because one's to the right and one's to the left. And so a grand total, if you're adding that up, would be an initial momentum of the system of negative 0.25. So 0.25 units of momentum, or kilogram meters per second of momentum to the left. And then afterwards, let's go and press play here and pause after they've collided. And we've got momentums of negative 0.63 and 0.38. Add that up. What do you get? Well, we get negative 0.25 still. Okay, so initial momentum, final momentum, the simulation is showing it as well. All right. So I'm gonna actually prove it to you in a second, but I mean, just basically the idea of what we're saying is initial momentum equals final momentum, and then this is the idea about the directions. So in a situation later on, when we have different directions, x's and y's and even z's in 3 dimensions, it's important to know later on. I'm just showing this to get ready for it, but we have momentums conserved, initial and final, and then if we're talking about momentum in a particular direction, the momentum in the x direction is conserved. And then if we're analyzing y direction momentum, it would separately have an equation just like this as well. And the z direction for 3-dimensional would separately have an equation just like this as well, right? With y subscripts all the way along for the directions and z subscripts all the way along for the directions and so on. Okay, so just be ready for that later on. You can't have the x's and the y's all in the same equation. It just doesn't make sense. Just like when we did vector work earlier on for just adding and subtracting vectors themselves. So is momentum really conserved? Is this true? Like, are we just being told this? Do we just trust that it's true? Well, let's look at a collision. All right, so we know in a collision there's going to be force of mass 2 on mass 1, and then there's also this force of mass 1 on mass 2, right? Well, those are actually reaction forces. Those are the same values. They're always the equal and opposite directions. Those are just equal and opposite Newton's third law action reaction forces. So if we analyze that, that would mean that force number 2 is equal to negative of force number 1. They're equal and opposite, right? And then if we were to use the second law to further analysis, we'd have ma, mass times acceleration, right? So we'd have mass 1 times acceleration number 1, right? What its acceleration is, and mass 2 times its acceleration, right? Just opposite directions because of the Newton's third law. And then further to that, acceleration is delta v over delta t. So we have the same delta t's because the time for the collision is just the same for both of them. And then if we multiply both sides by delta t, we simplify out, we get negative m times delta v for object 1, change in velocity for object 1, and mass 2 times its change in velocity. Well, change in velocity is final minus initial, right? Final minus initial. So v2 prime minus v1, final velocity minus initial velocity, and v2 prime minus v2. And so now what we do is we multiply out. So we get a negative m1 v1 prime right there. And we get a negative and a negative, so a positive m1 v1, and then an m2 v2 prime, and a negative m2 v2. And then we can just swap sides on the equation. So add an m2 v2 to this side, both sides really, and take away, and add, an m1 v1 prime to both sides, and it becomes the equation we've already seen. Okay, the m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. Right, so yeah, conservation of momentum is true. It's a consequence of Newton's third law, really, or at least was shown here using Newton's third law. So some possible results that we could have for this, right? So let's watch the masses equal video. So this is equal masses, equal mass carts coming in, and we have the red one coming in with a certain velocity. The blue one, I would say, appears to go out with that same velocity. The red one clearly stops. That's a reasonable takeaway from that video, right? Without even measuring the actual speeds. So we could have, say, this speed coming in is 3, and then the other one goes out with 3. Now, if you have the mass times the velocity, if say the mass was 1 kilogram, you'd have a momentum of 3 and a final momentum of 3, right? So momentum's conserved. It looks reasonable, basically, right? If we were to analyze the actual values and everything else, we are certainly, like we said, expecting this to be 3 meters per second, right? Based on our observations. And so here's our analysis. Momentum is conserved, so initial equals final, m1 v1 prime stuff, right? And so we have whatever the masses are, it doesn't matter, it could be 1 or anything. This just makes it so the momentum's not 3, instead it's a quarter of 3, so 3 quarters, I guess, right? 0.75. Yeah. And then, so we have the initial velocity of the one was 0. Which one was that? That was the blue cart was 0 velocity. And then the red cart ends up with 0 velocity. And you can see the math works out where this gives us the final velocity that we predict mathematically would be 3 as well. So the conservation of momentum concept is agreeing with what we're seeing from the video. What if we have a little mass colliding with a large mass? A little mass colliding with a large mass. So we've got the little red cart, so it doesn't have extra mass, so it's just 1 unit. This one is extra mass, so it's more, right? So watch what happens. So notice the large mass is going off with less velocity. The red mass rebounds backwards this time. So just 1 second, please. All right, sorry about that. Students come in at lunch sometimes. Anyway, so possible values for this small mass colliding, right? We could have a total momentum of 10, momentum of 0 to start. And if this one had, say, it was going backwards slowly, so maybe it's a momentum of -1. Well, what would this momentum have to be for that to be the case? Well, I think you're probably on to this where the -1 has to add with something and be equal to 10. So it would have to be 11, right? So let's look at possible values. So I'm going to set the masses as just 1 kilogram. And so it's going to be the same numbers, really. We have that velocity of 10 with mass of 1 giving us momentum of 10. The other one's going to be a mass of 2 kilograms. Okay, so that's the numbers, right? We got the 1 with the 10, the 2 with the 0, the 1 kilogram with an unknown, and then the 2 kilogram with an unknown. Okay, so let's say if this was -1 velocity, giving us that -1 we're talking about, right? Notice soon we'll be able to actually predict velocities of both. For now, we need an energy concept to do that. For now, I'm basically saying, like, if this one has a velocity -1, what would that one have? Okay, and so conservation of momentum would kick in. We'd just solve for the final velocity of the other mass, and it would give us a value of 5.5 meters per second. So this one going off with 5.5, the V2 prime, that's the slower velocity, right? Going off. Yes, that's the blue one going off to right with that slower velocity. Notice that slower velocity represents that large momentum of 11. Okay. So it was kind of messing me up. So it might be to you too. I'll mention it here that this being on the right in the equation, but really it's left in real life, was kind of weird, right? But initial and then final, analyzing both masses. So there we go.
Can Emma Buxcomb and Ruby Lynn please go to room 119?
I was going to pause the video, but it was short. Is it possible for a golf ball? Any golfers in the house, right? It's possible for a golf ball to end up with a higher velocity than the head of the club. Like, in other words, is it okay? Like, is that possible? Can momentum still be conserved in that scenario? So let's look at possible numbers here, right? So if we have the golf club head being 0.2 kilograms, which is realistic for a 1 wood, and we have the decimal 0.45 kilograms, which is the mass of a golf ball. If the club was coming in with 50 meters per second and it reduced to 30 because it's colliding, what speed would the ball have as a result? So we know conservation of momentum is a thing, right? Definitely true. And so we do our M1V1 stuff, plug in the numbers, and collect like terms and simplify and multiply things out and so on. We end up with a value for a final velocity of that golf ball, if this thing reduced to 30, that velocity of the golf ball would have to be almost 90 meters per second. Now, I don't think it actually reduces that much, but I mean, if it did, that's what the final velocity would be. So basically, this is showing momentum conservation is definitely possible. Like it's possible for the ball to go off with a faster speed, and that does not, that does not violate conservation momentum. That possibility is not ruled out by the reality that momentum is always conserved. Okay. And again, I'm not saying these are necessarily the numbers, right? So maybe the golf ball, maybe the club head reduces by less, right? But it certainly, could be possible. Momentum would still be conserved. So the high speed here of a collision, let's take a look here. So start over again here. We've got a golf club coming in, hitting the ball. Watch the ball compress as part of it, and so on. And in that frame right there, the ball is going away faster than the club, right? Going to the left faster than the club. Not by as much as my calculations, so I'm guessing the club head didn't reduce by nearly as much, but definitely possible. Momentum is conserved. All right, so that is our first step in analyzing collisions. Further steps are going to be, instead of just one dimension, of course, we're going to have 2 dimensions, so we're going to have to analyze the x and the y separately, and knowing that they're all conserved. Both of them are independently conserved. The other thing you saw in the video about them sticking together, we'll get to that eventually as well. So that's the journey we're on. So as always, thanks for watching. And if you have any questions, feel free to let me know, email me or post in that help post thing. All right, thanks.